When we think of a function, we usually think of this in an algebraic context. But since we're dealing with sets, I want to try and approach functions from a set idea. We talked about relations on sets. Well, now let's be more specific. A function from one set to another, let's just call them A and B, is a rule. And it's a rule with a particular assignment scheme, which assigns exactly one element of B to each element of A. So A is taken to be by our rule F. We sometimes write the function goes from the set A to the set B. I've just named my function F. Or we can say that F maps the set A to the set B. In this way, we're thinking of a map as a transformation. And we'll typically write that F of A is B. That's the notation we see algebraically. It is this part that makes a function special. A function takes a single output. There's only one possible B for any given value of A. In a sense, grades. A grading is a rule by which I assign to each student a value from the set I think these are all the grades that are available at Seton Hill. Um, Standard letter grades, an incomplete, a withdrawal. Some courses can be taken pass fail. Oh, right. There's satisfactory and unsatisfactory in some of those cases. But you pick a student in a particular class, you get to assign a grade. Each student only gets one grade. Um, Joey isn't going to get an A and a C plus in my course. He's only going to get one grade. I could have a formula, especially in functions whose originating set, I haven't given it a name yet, whose originating set is number. So I could say, we're going to say a function that goes from the set of real numbers to the set of real numbers is defined by taking a number and adding one to it. So this is the exact sort of algebraic function you've been thinking of, I would assume, since you first took algebra classes a number of years ago. Um, this, I hope, makes sense that no matter what number you pick, there's only one possible output based on that number. F of 7 is 8. F of negative 3 is negative 2. F of 1.372 is 2.372. F of pi is 1 plus pi. As long as I have a real number, I get another real number out. The set A is the domain of our function f. The set B is the codomain. I know that's not the word you first thought of. That's not what we normally call that. Well, that's not what we called it in algebra class. In algebra class, we had this thing called the range of a function. I want to define that a little differently. The range of a function is the set of b's in my set B so that there is an A with B equals f of A. Why is that different? Well, first of all, this is a subset of B. It might be all of B, but it is a subset of it. Uh, there exists A in A. I should specify that that A has to be part of my domain. Uh, for example, algebraically, the function f of x equals x squared. If I think of this as a function from the real numbers to the real numbers, well, no matter what real number you put in, you're going to get a real number out. But the range of f is actually never going to include a negative real number. Since we don't get any negative real numbers, the range is a subset of the reals, not the whole set. Uh, B is the image of A under F. Sometimes we reverse those. We think of A is the pre-image. Oh, you need to spell that right. P-R-E, image of B. Again, under F. So my function f takes things in set A to things in set B. It takes them in any reasonable fashion as pictures, right? If I've got numbers, I make a graph. But what is a graph? Well, really, a graph is a set. A graph is the set of x and y values for which the equation I have created is true. And that basically makes a graph a logic question. If I consider that same function x squared, but instead of going from R to R, it goes from Z to Z. Well, then the range of f is a particular set of integers. And what's more, the graph looks completely different because I've changed the domain. I've changed the function completely. This is an important but subtle statement, but the domain is as much a part of a function as the rule or the association is. And when I write this way, it becomes a different function altogether. Bottom of page 161, this is the graph of x squared in the integers. It's a very different picture. So it's important for us to realize that the domain is an inherently important part of what our function really is. Normally I'd say are there questions at this point, but you're not here to ask questions, so I can't. If I have two functions, and I need to be particular here, they have to have the same domain and codomain. Then I can add or multiply, provided these are numbers. If I can add, I can subtract. If I can multiply, I can divide as long as I don't divide by zero. We did all of this in algebra. If f and g both go from the set A to the set, well, we'll use real numbers for the moment. I can use any set of numbers. Then f plus g of A is defined by f of A plus g of A. And fg of A is defined by f of A, g of A, where I'm multiplying. So as long as I have the output of my function is numbers, I can treat numbers like numbers. You did this in algebra all the time. If you think about any polynomial, x squared plus 2x minus 3, that's really the sum of three different functions. It's really the sum of the function x squared and the function 2x and the function, oh, helps if you write that properly, and the function 3. And I'm adding those two and then subtracting this one. If you'd rather stick with just adding, then you can put the minus sign here. That works. So a function takes numbers to numbers, elements of one set to elements of another set, as long as we are specific about the idea that we are taking each input to a particular output. Please note this function takes every input to the number -3. That's not a problem. Each individual input has only one output it can go to. That's what we mean by the assignment being particular. Um, Functions can also act on sets. So, for example, if I have a function that goes from A to B and I have S, some subset of A, then I could think of the image of the whole set S. F of, and to make the notation different, I'll put the square brackets around S. This is not always done. Sometimes people will just write F of S. Is the collection of F of little s so that little s is in my set S. This is a subset of B, just like the range. It's, oh, I don't want to just do it to one number. I want to do it to a whole bunch of numbers. For example, I could want to take a function. I'm going to write this function in a weird way. For z, a point in the xy plane, we're going to define t of z, the transformation of z, to be, I have to remember exactly what this formula is, but I'll write it this way: z rotated counterclockwise by 90 degrees. So if I have a point anywhere in the plane, this is my point z. Over here, I have t of z. And all I did was I rotated 90 degrees around the origin. So my original point was over here, and I rotated until I got there. What if I took a whole picture and I rotated the whole picture? Well, that would be T of S, right? So if I had a picture, I could take the same function T and I could apply it to every point in this picture. See how I rotated the whole thing 90 degrees and I got my new picture? If this is my set S, this is T of S. If I have a numerical rule, f of x equals x plus 1, I could give you a set made up of some numbers. Um, let's pull a couple numbers out of thin air. 1, 2, 3, 4, 12. Then f of s is 2, 3, 4, 5, 13. There we go. So I can apply a function to a single spot, a single number, a single element, or I can apply it to a collection of elements. But the whole idea is that each input gets only one output. I tend to visualize functions. Now, normally in algebra class, I would draw this like a graph. I'm going to cheat. Here's my set A. It consists of these numbers. Here's my set B. It consists of these numbers. And my function is behaving like that. This is the function f. So I have another way of visualizing a function, regardless of what the sets A and the sets B are. As a matter of fact, I don't even need to give you a rule. I could just give you two sets. I don't even have to write them vertically. I can write them horizontally. I can write them in any weird order I want. I can think of the set A and the set B, and I can think of my rule going between them. And if I have particular elements, this B is f of A means the arrow went from there to there. It is possible that I could have lots of different values over here and lots of different values over here. And maybe both of those go to the same place. That's allowed. This one only has one output. This one only has one output. Before you freak out on me, remember we did do f of x was x squared. F of 1 is 1. F of negative 1 is also 1. They both go to the same place. That's okay. That's allowed. But this does mean that I should look at some of the properties of my functions. And I should think about what makes a function better or worse, nicer or less nice as I go through and examine functions. Again, if you've got a question, pause this video, send me an email, come to office hours this afternoon. We'll figure it out. A function is one-to-one. I will often abbreviate this as the number one dash the number one. If for all x in A, for all y in B, f of x, oh, no, that's not right. That's not a B. That's an A. F of x equals f of y implies x equals y. What? Oh, well, fortunately for us, that's actually saying this is not allowed. If you have two things that end up on the same dot, if the output is the same, then the inputs must have been the same. What's the contraposition of this? If x is different than y, then f of x is different than f of y. So only one thing can go to one thing. Aha, 1-to-1. Each thing over here only goes one place over here, and each thing over here only came from one thing over here. This is also called an injection or a univalent function. One value, univalent. Valence, like in chemistry, right? Valence ions and all those sorts of things. You'll hear this injection more often than univalent in these levels of courses. So this is what it means for a function to be one to one. I'll do some more in a minute. A function is onto if for all b in B, there exists A in A with f of A equal to B. Huh? Again, it's a direct definition, but what does it mean? This means every single element in the codomain is hit by something in the domain. If we think of the codomain, B, and our domain, A, no matter what element you pick over here, it had to get hit by something. No matter what thing you pick over here, there must be something that came from here to get there. Oh, this is spread all the way across. It covers it completely. We are on every value here. This is also called a surjection. Sur, meaning on, like sur la table, on the table. Another way to think of this is that the range of F is all of B. You're not allowed to miss anything. All right, I want to use this picture or pictures like that. Let's think about this for a minute. Let's suppose I have a function and it goes from A, B, C, D to the numbers 1, 2, 3, 4. So here's the set A, here's the set B. I am going to make a function that is not one to one. This function is not only not one to one, this function is not onto either because there's nothing that hits 4. There's something that hits 1. There's another something that hits 1. That's what's making it not one to one. These two get missed. That makes it not onto. However, same two sets. This function, that function is one to one. It's also onto. Oh, okay. Hmm. If I change the sets a little, I can get one and not the other. Here's a new function. This function is onto and not one to one. This function is one to one, but not onto. There are lots of functions that I can construct draw pictures for that satisfy one property or the other. But notice that our properties are universally quantified and existentially quantified statements. So if I really want to show that a function is one-to-one, or that a function is onto, and it isn't a function with finite, simple pictures, then I might actually have some work to do here. And it turns out that these are proofs I would have to do if I want to show something is one-to-one or isn't one-to-one. Um, Top of page 157. One-to-one and not onto. Onto but not one-to-one. Both. Neither. Wait a minute. Why is that one not a function? What's wrong here? A is assigned two distinct values. A function only gets one out for every in. This in has two outs. That's not allowed. So I need to be careful. By the way, a function that is both one-to-one and onto, a function f is a bijection if f is both one-to-one and onto. Well, bi means both, so it's got both properties. I'm good with that. Again, here's where I would ask about questions. We tend to think of functions as things that deal with numbers. And when I'm dealing with numbers, I tend to want to talk about the numerical values I'm taking on. So if I have a function that goes from A to B, where A and B are subsets of the real numbers, they might be the whole set of real numbers, but they're subsets of the real numbers at worst. F of x is strictly increasing if when x is less than y, f of x is less than f of y. Graphically, this means the graph is going up when we go from left to right. If I change this word from increasing to decreasing, then I change this inequality, but not this one. I want, as we go from left to right, I want the y values to get smaller. Again, graphically, increasing goes this way, decreasing goes this way. Why do I care? If f of x is either strictly increasing or strictly decreasing, we'll call that a monotone function. Then f of x is 1-to-1. Every function that either goes only up or only down is 1-to-1. Aha! This helps. Okay. In general, if I want to show a function is 1-to-1, I have to do a proof. I have to prove for all x, for all y, if you have the same output, you came from the same input. Now that's a proof. We can do it directly, we can do it indirectly, we can do it by contraposition, we can do it by lots of ways. But that's a proof. If I want to show that f of x is onto, I have to prove for every b in B, there exists a in A with f of A equal to B. In other words, prove you can hit everything. But these are universally quantified statements. So to show f is not one-to-one, all you have to do is find one place where two different values go to the same thing. To show f is not onto, you have to find one output that isn't hit by an input. That was what I did with f of x equals x squared. I said, hey, this is not one-to-one because f of 1 equals 1 and f of minus 1 equals 1. Can't be one-to-one. I found a counterexample. It's also not onto because f of x equals negative 1 has no solutions because our function was going from real numbers to real numbers. If I do complex numbers, then this has a solution, but that's not what the function said. Questions? The reason I want to know whether or not a function is one-to-one, or to know whether or not a function is onto, is to know whether or not I can undo it. A function has an inverse only when it is a bijection. The only way you can have an inverse function is to turn the arrows around. If you're going to turn the arrows around, first of all, you have to have all the arrows. And that means you need to be onto. Let me go back to my previous picture. This function is not onto. I don't have an inverse for 3. This function is not one-to-one, so if I try to take the inverse of 1, I don't know which thing to go to. Not onto, can't get back from C. Because this is both one-to-one and onto, I just have to turn the arrows around. F inverse of 1 is A, F inverse of 2 is D, F inverse of 3 is C, F inverse of 4 is B. I can only do this when a function is both one-to-one and onto. I could define a partial inverse if I really wanted to say, well, you can only do it for some of it, like for x squared. How do you undo a square? If I were there in person, I would be expecting a whole bunch of you to go, with a square root. But square roots are only defined for positive values. So we make a choice and we say, we're not going to use this one. We're only going to use this one. That sort of choice making is called a branch. There's a whole discussion in calculus and analysis about branches and branch cuts. My PhD thesis was related to this. We're not going to worry about that ever again. But I can only have an inverse when I have a bijection. If I want to know about more than one function, suppose I have f going from A to B, and I have g going from B to C. I could think of this as a picture. I have set A, set B, and set C. I go from F goes from A to B, G goes from B to C. What if I wanted to do this in one jump? I can define G of F from A to C by G of F of A is G of F of A, because A is going to go to some point B via F, and little b is going to go to some point C. This is composition. Now, I've written the composition of F and G. Technically, it is the composition of not and. This is not a symmetric relationship. It should be G of F. The order is important. Why is the order important? Well, because if I try to do F of G, well, G goes from B to C. F doesn't start in C. I can't go from here. So I have to make sure I'm going in the right direction. When our functions are on the same domains, it's even easier to see that the order matters. Let's consider f of x is 2x plus 3, and g of x is 3x plus 2, and we're going to define these on integers. By the way, these are both strictly increasing functions. They are one-to-one. I'm not worried about inverses. Don't care about that. But if I do f of g of x, f of g of x. So that's f of, plug this in, 3x plus 2. But f says take the thing you've put in, multiply by 2, and add 3. So take the thing you put in, multiply by 2, and add 3. Okay, I get 6x plus 4 plus 3, or 6x plus 7. Let's do them in the other order. G of f. Well, that's this. F of x says take the thing you put in, multiply by 2, and add 3. But G says take the thing you put in, multiply by 3, and add 2. So I'm going to take the thing I put in, multiply by 3, and add 2. Please notice that's 6x plus 9 plus 2, which is 6x plus 11. Those are not the same. That's important. G of f and f of g aren't the same thing. And that's a common occurrence in algebra. Figuring out, by the way, when f of g and g of f are the same, that's important, depending on what algebra you're doing. Page 159. Here's my picture for f of g. Top of page 158, there's my picture for the inverse. You see how we're just turning the arrows the other way around? If a function has an inverse, we're going to call it invertible. A function that doesn't have an inverse is not invertible. As I said earlier, a graph is a set of points that makes a function true. So I like functions that are graphable because I like to see pictures. But really, a picture is a set, and it's the truth set for the equation. The graph of f assuming that f goes from A to B. A is in A and B is in B. And it's really just a picture. But it doesn't have to be a picture in the traditional sense of what we are used to seeing as a graph. Lots of graphs can be thought of differently. By the way, there is an entire course called Graph Theory, which has nothing to do with this idea. It's a very different idea of what a graph is. If you're in computer science, you should take that course. If you're an upper level computer science person, you should take it next semester because it's offered and I think it's a cool course. Questions? Again, if you were here, pause this, send me an email, come to office hours, we'll figure it out. There are three functions introduced in the remaining pages on this chapter that I think are useful. I want to talk about the floor function. This is a function that goes from the real numbers technically into the real numbers, but the range of the floor function is actually integers. We define the floor of x is the largest integer less than or equal to x. Sometimes the word largest is replaced by greatest, and you'll often see this called the greatest integer function. Why am I calling it floor? Well, because what it really does is it takes a number and rounds it down. So the floor of 3.1 is 3. That's an integer. It's the largest possible integer that's still smaller than or equal to 3.1. The floor of 102.5 is 102. The floor of the square root of 7, well, the square root of 7 is 2 point something, is 2. The floor of negative 1.2. It's the greatest integer less than this. That's negative 2. By the way, the greatest integer of the floor of negative 1 is negative 1 or equal. The floor of 0 is 0. I really like this particular function because it rounds down. It's got a really nice graph. Page 162 here. Notice for all the numbers between 0 up to, but not including 1, the floor is 0. For all the numbers between 1 up to, but not including 2, that's 1 point something, the floor is 1. This is called a step function. I hope the reason for that is really freaking obvious. By the way, if you replace this idea, that's, by the way, why these are L shapes. You're really taking a pair of brackets and just taking the bottoms, the floors. If you round up instead of rounding down, you have the ceiling function. Ceiling of x is the least integer greater than or equal to 2x. So same numbers. Ceiling of 3.1 is 4. Ceiling of 102.5 is 103. Ceiling of the square root of 7 is 3. Ceiling of negative 1.2 is negative 1. Ceiling of negative 1 is also negative 1. Ceiling of 0 is 0. Just go up instead of down. I really, really like these functions. They are in most computer libraries, programming libraries, as floor and ceiling. I believe in C, it's floor of X and ceiling of X. Um, I think, which programming language was it? This is how old it is. I have not written a program since they were written in Pascal. Pascal is the great, 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 great grandfather of C. I wrote programs in years that began with 198. Been a long time. I outsource most of my coding now. I think it was Pascal that instead of using the words floor and ceiling, used round up and round down, but it's been a long time. Another function, this function is really interesting because it's defined in an unusual way, is the factorial of n. Now, I'm using n, not x, because this is a function that is defined from positive whole numbers. And it always returns positive whole numbers. So n take away 0. And we're going to define it as follows. N factorial is n times n minus 1 times n minus 2 dot 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 times 3 times 2 times 1. So you take all the numbers from wherever you start down to 1 and multiply them together. So 1 factorial is 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial, 4 times 3 times 2 times 1. These numbers get fairly big fairly quickly. As a matter of fact, um, these numbers get huge. 5 factorial is 120. 6 factorial is 720. 7 factorial is 5,040. 40320. I lose track after that. 362,880, I think. Let's check. I have a calculator. And not only do I have a calculator, I have a calculator that has a factorial button on it. If you hit the math button, this last header, PRB, has a factorial button. So if I want 9 factorial, hey, I got it right. I want you to notice something. I'm going to start with 70 and multiply my way down. That number's bigger than this calculator can handle. This calculator can handle numbers up to 10 to the 99th power. 70 factorial is bigger than that. These are not huge. These are not just huge numbers. These are mind-wrenchingly huge numbers. 60 factorial is 8 times 10 to the 81st power. For the record, I believe that is longer than the lifetime of the universe, measured in microseconds. These are huge. We're going to use numbers like this. We're going to use them when we work with moderately sized data sets. So these are important functions to know and important functions to work with. If you have questions, please come see me in office hours. I hope you had a wonderful day. Have a wonderful weekend, and I will see you all on Monday the 23rd. when we have our exam. Bye.